as I mentioned yesterday, and I did get all the videos posted with all the video notes posted, that we would do calculating electric potential from a set of points. So we're going to put a 5 nanocoulomb charge here, and we're going to put a negative 10 nanocoulomb charge there. And we're going to calculate two different electrical potentials. We're going to calculate one at A, and we're going to calculate one at B. And we're given that this distance between A and B is 0.08 meters. This distance is 0.05 meters. This distance is 0.05 meters. And we want to know the electric potential at A, and we want to know the electric potential at B. So just to remind everybody, we started out with Coulomb's law, and that's K Q1 Q2 over R squared. Then we said, well, I could do F divided by Q, and one of those charges, and I'd get a K Q over R squared, and we define that as an electric field. And now we've got potential is equal to K Q over R. And this one has no vector character. The other thing is K is equal to our 9 times 10 to the 9th. And our units are Newton meters squared, Coulomb squared. Yeah, for that. So if I do this for my units, so we're going to do our unit analysis here, I get Newton meters squared, Coulomb squared, coulombs divided by meters. One of those cancels, and remember a Newton meter is a joule. So this is going to be a joule coulomb, and we're going to define that as a volt. So we're going to get that defined as a volt. So that's just looking at our unit analysis so that we have that taken care of. Now, in order to do this, I'm going to have to know what these distances are. And we know what this distance is going to be, or we can at least figure that distance out. R is going to equal the square root of our 0.05 squared plus our 0.08 squared. And if I punch that into the calculator, and if I've done everything correctly, I get 9.43 times 10 to the minus 2 meters. And because this is an isosceles triangle, this distance is going to be the same. So we've got our configuration distances that are there. So how we're going to approach this problem is I'm going to calculate, so we want to find the potential at A, and my potential at A is going to equal the total potential from the 5 nanocoulombs plus the potential from the minus 10 nanocoulombs. So we're going to have to calculate that out. So we're going to get our V is KQ over R. And if I do that one, I get my 9 times 10 to the 9th, 5 times 10 to the minus 9. And this is at A, so I've got to use this R. So I'm going to have my 9.43 times 10 to the minus 2. And we've already shown that my units are going to end up being joules coulombs, which is going to equal a volt. So this is going to be 45 divided by 9.43 times 10 to the minus 2. And if I plug that into the calculator, I'm going to get 477 volts. And this was for my positive 5 nanocoulomb one. For my negative 10 nanocoulombs, we're going to use that same equation. I get my 9 times 10 to the 9th. And now I'm going to have my negative 10, and I have to keep track of my negative here, times 10 to the minus 9. Its R is that same R, so I get my 0.943 times 10 to the minus 2. So I'm going to get negative 90 divided by my 9.43 times 10 to the minus 2. And if I plug that into the calculator, I get a negative 945 or 54, sorry, 954. So my potential at that point, I just have to add them up. So I'm going to have my positive 477. I have a negative 954, and I'm going to end up with a negative 477. And that kind of makes sense because this one has got twice the magnitude of the charge. It's going to make negative because we're going to be there. And so we've got a negative potential in that spot. I can do the same thing for my potential at B. It's still going to be my total. It's going to be the 5 nanocoulomb one plus my 10 nanocoulomb one. Except this time when I punch in my numbers, I get V is K, Q over R. Except this is going to be the same. I get my 9 times 10 to the 9th. I have my 5 times my 10 to the minus 9. Except now I'm going to be doing my 0.05. So I get my 45 divided by my 0.05. And that equals 900 volts. And that's for my 5 nanocoulomb one. For my 10 nanocoulomb one, I get 9 times 10 to the 9th minus 10 times 10 to the minus 9, 0.05. I get negative 90, 0.05. That ends up being 1800, and it's negative. So now I get my total is just going to be my 900 minus my 1800, and I'm going to end up with negative 900 volts. So it certainly makes things a lot easier to negotiate. Lots easier to negotiate. All right. So let's do another quick one. We defined capacitance as equal to the charge divided by the voltage across. So if I've been given, I've got my capacitor here. And we have our battery. And we're told that this is a 12-volt battery. And we're told that it's going to store 35.0 microcoulombs, we want to know what the capacitance of that device is. Well, that one's a pretty straightforward calculation. We're just going to take our charge. We're going to divide it by our voltage. And we're going to end up with 2.92 times 10 to the minus 6. Now this is Coulomb volts. Okay. And we didn't actually say it, but a farad is equal to a Coulomb volt. So this we could actually write it as 2.92 microfarads. And the reason I want to write this out for you guys is if you're working in WebAssign, the box, double check and pay attention to the box, because it may give you those units of microfarads. And if it does this, I'm going to put in my answer of 2.92. But if it does, my box looks like this, and it says farads, I'm going to put in my answer 2.92 e to the minus 6. So just watch your boxes in WebAssign to make sure that you're putting in the right values just because of how they defined it. Okay, and now the problems everybody's been waiting for. Calculating equivalent capacitance. So I'm going to give myself a circuit here. And I want to know the equivalent capacitance of this circuit. This is going to be 5 microfarads. This is going to be 2 microfarads. We're going to make this 3 microfarads. We're going to make this 2 microfarads. We're going to do this one as 2 microfarads, 5 microfarads, and 3 microfarads. And we're going to make this one 10 microfarads. Okay, so now I've got a system here, and we're going to calculate. We want to remember that my equivalent capacitance for series is 1 over CEQ. And my equivalent capacitance for parallel is equal to all right, so first thing that we're going to do is we want to rewrite our circuit here to get rid of our parallels. So these are in parallel. These are in parallel. And these are in parallel. So if I'm going to do that, this is just 5 microfarads plus 2 microfarads is equal to 7 microfarads. This one is 2 microfarads plus 3 microfarads is equal to 5 microfarads. And this one is 2 microfarads plus 3 microfarads plus 5 microfarads is going to equal 10 microfarads. So I can redraw my circuit now into an equivalent circuit. So now I've got my equivalent circuit. And so now this one is 5 microfarads. This one is 10 microfarads. This one is 10 microfarads. And this one is 7 microfarads. Now these are in series. So I'm going to do 1 over CEQ is equal to 1 over 7 plus 1 over 5 plus 1 over 10 plus 1 over 10. So now I'm going to get, I get 1 over 7 plus 1 over 5 plus 2 over 10. Well, that's good because that's going to help me out a little bit. So I get 1 over CEQ is equal to 1 over 7 plus 1 over 5. And we said we have 2 over 10. But we know that this can actually be rewritten as 1 over 5. So that's great. So now I get 1 over 7 plus 2 over 5. Got to get my lowest common denominator. So I'm going to do my 5 plus 2 times 7 is 35 on the bottom. Okay. So I get 5 plus 14 divided by 35. So I get 19 divided by 35 is 1 over CEQ. But I need CEQ, so I'm going to get CEQ is equal to 35 divided by 19. And now when I plug that into the calculator, I get 1.84 microfarads. Now, this is the place where people get a common mistake in WebAssign, because a lot of times you'll calculate that, your 19 divided by 35, and that'll be 0.54, and you plug that into WebAssign, and WebAssign gives you the, that's not the right answer. But if I take the inverse of that, I'm going to end up with that number. And that's how you actually work through these kinds of calculations. So we're going to do another one. And we're going to take it a little further this time. And it's going to be a lot like your homework problem that you have in WebAssign. So we're going to start with, now capacitors are represented by flat lines. Batteries are represented by that kind of a line, where this is my positive and that's my negative. So we're going to set up a circuit here. And we're going to use some funky numbers so it matches what you're running into in WebAssign. And WebAssign says that this is going to be 9 volts. This is going to be 28.2 microfarads. This is 28.2 microfarads. This one is 22.2 microfarads, and this is 6 microfarads. First step is we want to get the equivalent capacitance of the system. So we're going to do our parallel first. That's going to be our 22.2 plus 6, and that's going to give me 28.2 microfarads. And so now my system looks like this. I got my 9 volts here. So now I have them in series, so I get 1 over CEQ is equal to 1 over 28.2 plus 1 over 28.2 plus 1 over 28.2. And that's going to give me 3 divided by 28.2. CEQ is going to be my 28.2 divided by 3. And I end up with 9.4 microfarads. So we've calculated the equivalent resistance for the whole thing. But then they want us to find the charge on each capacitor. All right, so to do that, to find the charge on each capacitor, we know that Q is going to equal C times our change in voltage. Each one of these is 28.2, or our equivalent capacitor for our whole system. So I'm going to get my 9.4 times my 9 is going to give me a charge of 84.6 coulombs on each one of these. Now, those are 28.2s and 28.2s. So if I'm going into my WebAssign, it says 28.2, 28.2, and then I got a 22.2 and I got a 6. I've got to deal with this. This is going to be my 84.6. This will be my 84.6, but I got to do something different for that. And what we know there is my change in voltage across this one is going to equal my charge divided by my capacitance. This gives me my 84.6, and these are micro, sorry, those are microcoulombs. This is my 84.6 microcoulombs divided by my 28.2 microfarads. This gives me 3 volts. So this one now is going to be my 22.2 times my 3 volts, which is going to give me my 66.6 microcoulombs. And this gives me my 6 times 3 is going to give me my 18 microcoulombs. So that's how we get the charge on each one of those that we're working with. We now want to find the potential difference across each one. And we already did that. That was our change, and our potential is Q divided by C. And each one of those had 84.6 divided by our 28.2, and that gives us our 3 volts. So across our 28.2, our 28.2, our 22.2, and our 6, each one of those is going to be 3 volts. Each one of those is going to get that for you. And if we wanted to take the energy stored for the system, our energy stored is going to equal 1/2 the equivalent capacitance voltage squared. So we already calculated our equivalent capacitance, and that was 9.4 microfarads, and our voltage was 9 volts. And that's going to give us, and this will end up being microjoules. This gives us 42.3 microjoules would be the energy stored in our system. Oops, I forgot to square it. That's not the correct number. It's actually going to be 380.7 microjoules. I forgot to square my 9 volts when I punched it into the calculator. So the problems aren't really all that hard. You just need to take them and break them down by our systems. So you look for what's in parallel first, and then you can redraw your system to figure out what's in series, and then just work through those calculations. So questions.